Hi everyone, welcome to this lecture number 2 of week 12 of the course on linear systems theory. In lecture number 1, the aim was to introduce you to some computational tools that would help you solve some basic matrix inequalities, starting from the Lyapunov inequality in continuous time to discrete time, stabilizability and so on. So, today what I will teach you is some computational tools that you would that would be helpful in solving these kind of LMIs. I will also run you through a few examples or through tests or few test cases of formulating problems as LMIs. I will briefly touch upon the linear matrix inequalities related to time delay systems. We will derive or we will see how stability of time delay systems can be formulated as equivalent LMI problems and see if the systems are independent of delay, depending on delay and so on. Similarly, with another concept called passivity of linear systems. Of course, delay systems by itself is a vast course. There are a bunch of books, bunch of literature on that. So, this is not a comprehensive or even a small introduction to delay systems. Neither is it a good introduction to passivity related concepts, but we will just learn little things that we may need and how we actually attempt to solve problems from different domains. Neither is this week's lectures an extensive introduction to LMIs, right. There are also a bunch of books that are available, lot of literature, lot of research work still going on, but it is just to expose you to certain tools which might be useful for you if you are pursuing your research activity or reading some other papers, or just if you want to look at some areas which are related to what we learned in the course. So, the aim of the course or aim of this week's lectures is not really to give you a comprehensive introduction on LMIs, is neither to do with delay systems nor to do with passivity or the other things that we are about to talk in this lecture. So, it is just to give you a brief idea on how to use tools of this form. Okay. So, before we start, so just a little properties of LMIs that I would like to list out is the following. So, if I say that fx is greater than 0, this is equivalent to saying minus fx is less than 0. Similarly, fx less than gx is equivalent to saying fx minus gx is less than 0. If fx is less than 0, sorry, f1x is less than 0, f2x is less than 0, this is equivalent to saying that the diagonal of f1x, f2x is less than 0. Similarly, if I have LMIs in two different variables, so I have f of x is less than 0, g of y is less than 0, then I can say that the diagonal of f of x and g of y is 0. Similarly, if this LMI is feasible, then this LMI is also feasible. You could just check by pre and post multiplying in this way, A, B, C, D with 0, I and 0, right. This is like, so these two matrices, this matrix and this matrix would have some kind of equivalence relation as we talked about in lecture 1 while we were deriving shear complements. Okay. So, again start with the example that we did in lecture 1 using shear complement of this block. Okay. So, I am about to solve this LMI where I want to find what is the region for which f of x is greater than 0. Okay, so, based on two different methods that we learnt in lecture 1, well, we see that the feasible region is just the interior of this unit disk and will look something like this. Right? This is straightforward to check. In addition, if I impose a constraint that, okay, in addition to just fx being 0, I impose another condition that x1 plus 0.5 is greater than 0, right. So, the LMI would change now to something like this. Okay. So, it is easy to check, right, that I am only looking at regions where x1 is now greater than minus 0.5, right. So, this the region to the left of this will no longer be the feasible region, and so solving for this LMI now would give me an appropriate feasible region, which in addition to this constraint also takes care of this particular constraint, that x1 plus 0.5 should be greater than 0. Okay, so LMIs can also be used to solve more kind of interesting problems. Much of the design problems that we looked upon were, okay, first stability was important, and second was design in terms of pole placement, right. So what we will do here is, again, this is not really a comprehensive introduction to what is called in literature as D stability or even DR stability. So suppose, okay, let's work in the discrete time case for the moment, that so I have x k plus 1 is a x k plus b u k. The standard stabilization problem would be find a control law u of k is k times x of k such that the eigenvalues of a plus bk are the eigenvalues are in the unit disk, right. And then we know now how to first formulate this as an LMI. That is what we learned in lecture number 1. Again, I am just dropping the case, the minus k here, which we would usually use, but nothing really changes. Okay, so suppose now, so my usually I am not really looking at as stability. In addition to stability, I am also interested in performance, and performance usually translates to placing poles of my closed loop systems at appropriate locations. So let us say, can I say maybe I want my poles to lie within this region here, or maybe some region like this, or maybe like this, or there is several possibilities, or say I just want my poles to lie within a circle of say radius 0.1 instead of 1. Right. So, so these problems are called D-stability regions. Well, in the continuous time, it could just translate to say your closed loop poles being say to the left of say minus k, for example. It could also translate to poles being say within this region where you put certain restrictions on the damping. If you put certain restrictions on omega n, then you will have another region, and so on, right. So equivalent concepts also exist in the continuous time domain. So let's look at, for example, this particular thing in the discrete time case of how do I solve for my poles to be in one predefined region of the stable region. Okay, so let's look at the autonomous system to begin with. And okay, so a DR region is defined by this following relation, right. So in the z plane, so I have matrices R11, R12, R22. Okay, the DR region is now represented by this particular LMI, right, where okay, so so R11 and R22 are of these dimensions, and overall I can write R as a partition matrix of this form from R11, R12 is symmetric, and you have R22 here, right. Okay, so what is the definition now? That the matrix A is said to be DR stable if and only if all its eigenvalues lie in the DR region defined by 1. And what defines these regions are this choice of matrices R11, R12 and R22. I will show slowly, or I will shortly show you some examples. So if I say, well, this my DR region looks something like this. So this is my DR region. Okay, so my system would be stable, or my system I would call it DR stable if in addition to stability all eigenvalues are within this shaded region here. So I am restricting my closed loop poles to certain sub regions of the stable region in the unit disk, and the stable region is the unit circle. Okay, good. Some properties, the DR regions are symmetric with respect to the real axis, as is case with in any general LMI regions. Okay, so few examples of what are these DR regions. If I take a very simple example of say R11 being -1, R12 being 0, R22 is -1, this will give me the standard unit disk, or the just this the general stable region. Okay, some other examples. So if I just add a constraint saying that the real part of z is greater than 0.6, then okay, if you just add it in addition to the constraints here, then I get that this is my new DR region, right, the region in blue here. Similarly, I can restrict to several other regions of the z plane or of the unit disk, right. So all these constitute DR regions. So now how to check? So okay, again there are a bunch of results that you can obtain by choosing this appropriate R's. You could also say, well, can I have my DR region as a circle centered at 0.1 with a radius of 0.1 and so on. So the literature that is at the end of the slides will guide you through little more exposure to these kind of DR regions, but it's just to give you an idea of what kind of problems then we can solve by formulating them as LMIs. Okay, so what is the LMI here? How do I check, given a A matrix and given a certain DR region, if that particular system represented by an A matrix is DR stable or not? So one result that says, okay, it's from a reference that is mentioned towards the end of the slides, is that a matrix A is DR stable, and this DR stable, these regions are defined by this choice of matrices R11, R12 and R22. So it is DR stable if and only if there exists a positive definite matrix P, also symmetric, such that any relation like this holds, and this is usually the Kronecker product. Kronecker product between two matrices. Right, so in general, if I say A is a two-dimensional matrix of the form A11, A12, A21, A22, and say B is also a two-dimensional matrix, A Kronecker B would be something like this, that you have A11B, A12 times B, A21 times B, A22 times B. Okay, so this is the LMI that we would be interested in solving. We can also formulate the problem of what if this LMI, if the answer to this LMI is no. So for example, I ask a question, so given an A, okay, is it DR stable? DR stable, say that I am only looking at not the unit disk, but say a disk of radius 0.1 centered at 0.1, right. So I am not interested in the stability region, but say some region like this. Okay, so if the answer is no, then I will look at an alternate problem, right. So I will look at, say I have xk plus 1 is A xk plus B uk. Now can I find a u equal to kx such that A plus bk is now DR stable, and these problems are called DR stabilization problems. Okay, so I will not go into the details of that. It's again an exercise which is similar to what we did for stability of or stabilization of discrete time systems using Schur complements and so on. But I will, again, you can just refer to the literature at the which is mentioned at the end of the slides. Okay, so now okay, how do we solve this via using Matlab? So a couple of tools that would be useful. Okay, there is also this LMI toolbox in Matlab, but I would prefer using these two. You may just want to download these two software packages called YALMIP, and Sedumi, just add those folders to your Matlab file, your Matlab path, and then things will be good. Right. Okay. So the first thing. Okay. Let's start by solving a very simple problem of stabilization, or not stabilization, but even say stability problem. So, for example, check whether a given A is stable. Check whether A is stable. Okay, it could be a continuous time and discrete time both. Okay, so what? Okay, I'm just at this YALMIP website. So there are a bunch of tutorials which you can go through. So ours comes in the category of semi-definite programming. So okay, so start from here. So I have a linear dynamical system x dot equal to Ax, and the Lyapunov condition says that I need to solve for A transpose P plus Pa less than 0, with P is a symmetric matrix which is greater than 0, and so on. So okay, so how do you define? So A you can just write in the standard Matlab way as defining a matrix. P is called an SDP variable. I am solving for P, so that will be called an SDP var of so it's will be of dimension 3 cross 3. The LMI that I am really trying to solve is F. So I just write down these two constraints in the code: P greater than 0, and then A transpose P plus PA is less than equal to 0. Okay, so there is a little warning which YALMIP tells us that okay, we are not really solving for strict inequalities, although theoretically we are looking for strict inequalities, right? That P should be strictly greater than 0, A transpose P plus PA should be strictly less than 0. So to do this, what we could do is just add a little some kind of a threshold to P, that just do not check for P being greater than 0, but instead say check for P being say greater than point. So the condition which YALMIP checks by default is this one, but you could also check for P being greater than or equal to 0.001, right? Just to add to this strictness here. There are also other ways which these guys tell us, okay, you can have the trace of P to be 1 and so on. Okay, so so once you write these constraints, P f is such that P is greater than 0, then the way to solve is you just say optimize f, and then the feasible value of P would be the value. So you have to write value of P, right, because P is just this variable here, and P feasible, while you just type down value of P, it will give you the appropriate value of P. Okay, so let's do some very basic code here. Okay, so I just go to the very standard problem where A is given as say something very simple, right. So A, let me start with this A as 0, 1, minus 1, minus 1, and of course it's easy to really verify that this is stable, but I just run this code for you and check what Matlab actually gives you, right. So it actually tells you that this problem is solvable, and you could also check for P feasible. So the matrix P that solves this problem will be given by this. So you can check that this matrix is symmetric and it is positive definite. Okay, so let me just do something else, right. Let me just add some. Okay, so this is unstable, right. So A is now instead of so I just take another A which is 0, 1, 1, 1. Okay, and check how this LMI solver throws up the instability clause for me, right. Okay, so I go through this process again, and it actually tells me that it gives me an infeasibility thing, right, that the problem is actually not solvable, and this because it's an unstable system, that there is no P that will solve the linear matrix inequality. Okay, and just to add a threshold, I just put as P as greater than or entries of P greater than 0.001. Right. Okay, and this is how just write the little code. Okay, now let us go one step further. So if we let me just open the slides of lecture 1. Okay, in lecture 1 we had this stabilization problem, right. So, how do I check if A plus Bk is a stability matrix? So, we kind of found out that the standard A transpose P plus Pa does not work because of these two unknowns k and x. Okay, so and then we had an equivalent LMI formulation for that, right. So, Ax plus xa transpose Bn n transpose Bn, where k was eventually given by this one. Okay, so we will try to solve a problem like this using Matlab. Okay, so so I just take this unstable A here 0 1 1 1 which we had here, and say let B is 0 1, and I need to search for a k or find whether or not a k exists such that this system is stabilizable. Okay, so my p is usually okay, the p I do not need anymore. So, my x is again a 2 cross 2 matrix is my SDP variable, right, again going back here, right. So, x is what I am solving for, and p is just x inverse that I can easily find out. N is of dimension 1 cross 2, right, this is also an SDP variable. So, there is no real constraint on A, right. So, on n, right, I am not really fixing n to be all entries to be greater than 0 or whatever. Only thing that is to be fixed is for x, and then my so this LMI I just plug into this equation, and I say optimize f, and then I have this p feasible or what, okay, the feasible x is this, maybe I should call this x feasible instead of p. Okay, and then I find this value of k, right. I just run this little code, and it gives me okay, let us check if okay, something went wrong. Okay, I should call this x feasible instead of p feasible. Okay, let me run this code again. Okay, so it gives me this values of k, right, and I can easily check what are the eigenvalues of A plus B times k, and you can see that the closed loop system is actually stable, right. Okay, so this some very basic examples. You can try out discrete time version of this, you can try out Schur complements and so on, but I'll just leave that to you. It's just a matter of typing down the code. Okay, a few more examples I would like you to quickly do here. So, first is the delay LMI, and what does this delay LMI do? So, let us take a small problem, or how do we motivate ourselves to do this problem of why are delays important. Let us say I have a plant x dot is a x plus bu. So, this is my plant. So, this is x dot is a x plus bu. Let us say I measures all the states, this is my input, and typically I will have a k here, okay, which will just measure, this will be measured instantaneously, the control law will be computed and then fed back, all will happen instantaneously. But in practice things may be a little different, right, that you may there may be some computation time, if you are communicating via network channel, that will cause further delays and so on, and therefore your closed loop control law may not be instantaneous. So, if I say I am looking at u equal to minus kx, okay, just may put this t's here, x dot t is a x t plus b u t. Okay, if in the standard case u of t is k x of t, and my system looks like this, a plus b k x of t, and these problems I know how to solve. If a plus b k is stable, then my closed loop system is stable. Okay, now usually u may not arrive instantaneously, and it may arrive with some delay. Let me call this tau. Okay. Under this situation, how does the closed loop system look like? I have x dot is a x plus b u, which is now k x t minus tau. So, this will be a x plus b k x t minus tau. It is no longer in this form, right. So, the eigenvalues of a plus bk would not tell me much about the closed loop system. So, in general we can write a delay system of the form x dot t is a x t plus let me call this some a d x t minus tau. Okay. So, okay, when is this system stable is the question. Okay. So, first the necessary condition is that the system without delay should be stable, right. So, the system without delay which means tau equal to 0 is stable or it should be stable. Sorry. And that is a plus bk or a plus ad first must be a stability matrix. Okay. Then we can ask ourselves a few questions, right. Is the system stable independent of delay? That okay, no matter whatever the tau is, my closed loop system will still be stable. We will see if that could be true, or derive under what conditions these systems are actually stable independent of the delay, means whatever even for large delays my system would still be stable. There could be cases where my system can I can guarantee stability, say if the delay is like say 2 seconds or say 4 seconds, but anything larger than 4 seconds I might go to the verge of instability. Okay. So, let us see how we can actually quantify those results. Again, as I warned you that this is not really an introduction or even it is not even introduction, you know, forget about a comprehensive review of delay systems, but it just like just teaching you a bit of how to formulate problems as LMI problems. Okay. So, what is the result that we will be interested in? Okay. So, I start with x dot equal to ax plus bu and I write a delay system which is of this form. The initial conditions now need to be defined on all this time interval from minus tau to 0. So, just to solve a continuous differential equation I need just x of 0, whereas to solve a differential equation I need the set of all initial conditions which happen in this range or in this time interval minus tau to 0. Of course, okay, I will not go into the details of that. I will also assume that the delay is bounded from above. One more assumption we make is that the delay is constant with time, but there are also results where you can say that my delay changes with time, and then you will say how fast it changes, how slow it changes and so on, but we will restrict ourselves to a constant delays. So, this system okay, we will call it system 2 is asymptotically stable if there exist symmetric matrices P and S such that P is greater than 0 and an LMI like this holds. Okay. The stability certificates are again obtained by making use of a Lyapunov like function. So, this was the standard Lyapunov function for the system without delay. So, now we have another term which takes care of how to handle the delay terms. Okay. So, let us see if we can really quickly do a proof on how we arrive at this delay LMI. So, I have V of xt is x transpose px plus integral t minus tau to t x transpose tau as x tau d tau. Okay, then I do the differentiation v dot of xt again along the system trajectories. What are the system trajectories? The system trajectory x dot is ax plus ad x of t minus tau. Okay, so I just do the standard differentiation. I get this is x transpose a transpose px plus x transpose t minus tau a d transpose px plus x transpose pax plus x transpose p AD of x t minus tau plus x transpose S x minus x transpose t minus tau S x of t minus tau. And I rearrange terms in the following way, right. So, I have x of t here, I have x of t minus tau with a transpose. What I am left here is this A transpose P plus PA plus S. I have a PAD, this transpose of this A transpose P minus S x of t minus tau, that this should be less than 0, right. So, x of t this with this constraint and t greater than or equal to 0. So, v dot of t being less than 0 translates to this matrix being less than 0. Okay. Now, this is an LMI, right. So, look at this. So, this is what I am interested in solving. P greater than 0, again matrices S which are also positive and symmetric such that this LMI holds. Okay. So, I will just quickly show you some examples again. Okay. So, okay, let me go here. So, let me comment this out. Okay. So, what I will be interested in is to check for stability of this particular delay system. X dot of t is minus 1, 0, 0, minus 2 x of t plus 1, 0, 0, 1 x t minus tau. Okay. And if I just run this code here, so I just plug in, so my unknowns are p and s of they are 2 cross 2. So, what I need to check is I just plug in the LMI condition here, that is p greater than 0, A transpose P plus PA plus S and all this entire matrix, I just plug it in here. So, P is greater than 0, S is greater than 0 and this dm which is the matrix inequality which we had. So, this also this should be less than or equal to 0. I just run it for optimizing f and this is what I get. Okay, I get an error. Okay, I forgot to define the A. So, my A was minus 1, 0, 0, minus 2. The AD was just the identity, that is 1, 0, 0, 1. Okay, and let's see if this works. Okay, so I get I can just check the eigenvalues now of P feasible. Oops. Okay, so P is positive. Similarly, I can also check for the S feasible. Okay. So, this means that this the system governed by this dynamics with this particular A and AD is stable independent of delays. Okay. Now let me do something else. So, this comment this out and go to some other example where, okay, let me write down the problem properly. So, in this example, so x dot is -2, 0, 1, 0, -3, 0, 1, 0, -2, xt plus -1, 1, 1, 2, -1, 1, 0, 0, -1, x t minus tau, and check if this system is stable independent of delay. Okay, so let us see. So, I just plug in the A and AD. So, my matrices are now unknown matrices are of dimension 3 cross 3, and I just run this code. Okay, just that actually gives me an infeasible condition here, right, that this system is not independent of delay. So, the answer is this system is not stable independent of delay. Okay, whereas this system actually was. This actually was stable independent of delay. Okay. Now, the next question that we will ask is, okay, is it stable say maybe for some small delays? And then we ask the question, how small? Okay. So, let us see if there are results which tell us that, right. So, the delay dependent stability, okay, I do some model transformation. I'll skip these steps. So this system is I do a system transformation here such that when this system is stable, the original system is also stable. X dot t is a x t plus a d x t minus tau. So, if this is stable, this is also stable. The converse may not be true, and therefore, this transformation adds a bit to the conservatism of the results, but okay, we will not at the moment worry about that. So, this system is asymptotically stable. Okay, it should be 2 here. If there exists matrices of this form such that I have an equivalent matrix LMI of which looks like this, right. So, unknowns here are P, S0 and S1, where M has this term tau now. You see there is some dependency of the LMI on the delay term tau. Okay, this can be, you can just solve for this V dot. Okay, I will not go to too much of the details, but okay. So, the delay term explicitly appears in the LMI in form of this M, whereas in the previous case there was no delay term, right. So, all these terms were independent of delay, right. So, okay, now let us check if this same system, if this was stable independent of delay. Now, let us just check what happens for say small delays. So, I just put a delay of say 0.1 and I just plug in the code. Okay, so let us see what happens. Okay, so this okay, this looks good. So, there is no infeasibility condition. So, for 0.1 the system is stable. Let us say now I go to say 0.3. Okay. still seem to be good, right. So, there is no infeasibility condition here. Now, let me say okay, say D is say 1. Oh, no, some infeasibility condition, right. So, two things that I found out was for point 1 it is stable, point 3 is stable, and for 1 or for tau equal to tau or D whatever tau equal to 1, the system turned unstable. Okay, and then maybe you can just write a little loop to check for what is the maximum value of tau or D that the system is stable. So, it will be some 0.4 or things like that. So, we can just play around with the quantum of delay and check whether or not the system is stable. So, what is the observation here? Even though there are some systems which are stable independent of delay, some systems are stable well depending on for some small values of delays are acceptable, say in this case 0.4 seconds, but for larger values my system goes to the verge of instability. So, this is a little better result than what we had previously, right. Okay, the last thing is about passivity. Okay, so this is something which is which we kind of do very often, but we do not really think that this is, or we do not work within the realm of passivity, within the concept of passivity. So, I start with an input output system. Okay, some typo. X dot is Ax plus Bu, Y is Cx plus Du. Just define a supply function which is quadratic and say Q is of this form. Okay, so as this system is with say some 0 initial condition, or okay, not necessarily, but so for ease of representation. So, this system is said to be passive with respect to the supply rate if and only if something like this, some relation like this holds. Okay, so what does this mean from the physics point of view? Okay, so let us do things in a way that we can understand. Okay. The system is called passive with respect to some supply rate. It is actually the physical supply, say some power supply you can call supply rate, if there exists a function called the storage function, because X is the state space, right. So, all X come from X. Okay, okay, so some typo here called storage function, so that for all initial conditions xt with xt not equal to x naught belonging to X, right, at any time t0, and for all allowable input functions, right, and for all t1, okay, so this should be t1 greater than t0, the following inequality holds, that the value of the storage function at time t1 is less than or equal to the value of the storage function at time t0 plus some supply rate. Okay. Now, I can just write a slightly better looking differential version of this one, right. So, that S dot is less than or equal to the supply rate. Okay, this will not be here anymore. And for the LTI systems, okay, this is just simply quadratic. The storage function is just of the form x transpose px, very similar to the Lyapunov function, and actually has very direct consequence also to the Lyapunov thing. Okay, so what is the interpretation of this? That ST1, S at T1 minus S at T0 is the stored energy or the rate of change of energy, okay, is equal to the supplied energy plus the dissipated energy. That is what any physical system would obey, right. It is just the simple law of conservation of energy. Okay. So, I will do a very small example of a passive system. Okay. So, just take a R with some voltage source V. Okay. So, this R, L and C are all passive elements. We can extract only a finite amount of energy from these systems. Whereas this voltage source is not a passive element; it is an active element. Okay. So, let us see what are we looking at here when I talk of passivity. Okay. So, the dynamics of this would be V is, okay, let me call this IL, the voltage across this as Vc. Okay. So, V is I R L dIL by dt plus Vc, and what is this Vc? Vc is simply C dVc by dt. Okay, so I can write an equivalent state space form of in the following way. So dVc by dt dIL by dt is 0, 1 over C minus 1 over L minus R over L. I have Vc IL plus 0 1 over L times Vc, and let us say that the output is just IL. Okay. Now, okay, what is the total energy of this circuit? The total energy is half L I square plus C V square, and if I take what is ds by dt along this dynamics, okay, so this will be L IL dot plus C Vc dot, and I substitute for IL dot and Vc dot from here, and what I get is the following. So this is minus IR square plus IL times the input voltage. Okay. So this is exactly the passivity relation, right, or the energy balance equation that we had here, that the stored energy is supplied energy plus the dissipated energy, or the rate of increase of stored energy. So this is my power dissipated, and this is just my input power. Okay. Now, okay, so if the system is controllable, then passivity is equivalent to solving the following LMI. Okay, so look at this little carefully. So how do we derive this condition? So just starting from here, so what I am looking at is S dot minus this supply u comma y is less than 0, less than or equal to 0. Okay, so let us start from this. So I have x dot is A x plus bu, y is Cx plus du. Okay. My storage function S of x of t is say x transpose p x. Okay, let me leave out the half for the moment. Okay. Now what I should find out is how does x s dot x t minus s u comma y, this is should be less than or equal to 0. Okay, so first let us look at this term. S dot is so I get x dot p x plus x p x t. This is so this is x transpose A transpose plus u transpose b transpose p x t plus I have x transpose t p, this will be an x dot here. This is A x t plus b u t. Okay. So this I can club it in the following way. So I have x u transpose x u. So okay, what do I have here? I have A transpose p plus p a, and the term involving x transpose and u would be p b, and the term involving u transpose and x is b transpose p and the 0 here. Okay. And what is my supply rate? So the supply rate, the way I define is in the following way. This is y u 0 1 1 0 y u. Okay, so let us do this. So, y, what is y? Y is Cx. Okay, so let's write down this first. So, this will expand this transpose. So, y u 0 1 1 0 y u. Okay, let us just make it a little scalar system, right, so that notations would be easier. So, I have this u transpose y plus, in general this will be y transpose u. Okay. Now, u transpose y is what? Cx plus du, again y transpose, this will be x transpose x transpose c transpose plus u transpose d times u. Okay. So, I can write this, so I just plug this in. So, I will have again terms relating to x u with the transpose and x u. Okay. So, I have terms relating to u transpose c. So, I will have a minus c transpose, there will be a 0 here, here will be d plus d transpose. Okay. So, I just subtract it here. So, what I get is now the following, a relation which looks something like this. Okay, this will just be a c. Okay, Pb minus c transpose, here this will be d, okay, because of this minus here, and this must be less than or equal to 0, and therefore, this is equivalent to saying that this is less than or equal to 0. That is essentially what I have here. Right? Okay, so some things, x transpose c will have a c transpose and a c here. Okay, so this will be c transpose, this will be c. Okay, so this is how I derive that particular LMI. So to check whether or not a system is passive, I just plug in this inequality, right? And of course, there is a bunch of literature on what can we do with passivity, how does passivity relate to stability, and so on, and how also we can do things related to things called passivity based control and a lot of it. Again, the idea is not to really go deep into concepts of delay or passivity or even DR stabilization and other stuff, but it is just to give you some idea of what you can do with LMIs and why do we need LMIs, starting from the Lyapunov equation to the stabilizability conditions, and then there is a bunch of stuff that you could do, and we just play around with some of these equations or these systems. Okay, so that kind of concludes what I had to say in this course of 12 weeks. I hope the course was useful to you. That was just to give you a little introduction to some higher or advanced level courses in control theory. This might give you a way to maybe pursue courses in optimal control or nonlinear control and a bunch of other things that will open up for you. I hope you enjoy the course and thanks a lot.